Question 8. The mass of Jupiter is 1.899 times 10 to the 27 kilograms, and it says the mass of Saturn is 0.3 times the mass of Jupiter. So it's saying that we want to try and find an estimate for the mass of Saturn. So Saturn here is 0.3 times the mass of Jupiter. And we want an estimate. So what I would do is, I would say 0.3, 3/10. I don't think I would change that necessarily. And I would put 1.899. I think I would go with 1.9, or maybe let's try 2. I think that seems reasonable enough. And then what we've got here is 3 times 2 is 6. Don't forget, estimates are all supposed to be things that you can do simply. 6/10 times 10 to the 27. And we know what 6/10 is. 6/10 is 0.6 times 10 to the 27. And you know it's got to be in standard form, and you should be okay with your standard form. 0.6 is 6 divided by 10, i.e. 6 times 10 to the minus 1, because don't forget, something to the minus 1 is 1 over that value. So we've got 6 times 10 to the minus 1, which is 0.6, times the 10 to the 27, which was here. And then using our rules of indices, we've got minus 1 and 27 gives us 6 times 10 to the 26. So that would be my answer. Now, depending on your individual take on this question, I rounded up here, so I would therefore have an overestimate. And you just say, because I rounded up. I'm not going to write the whole thing out. If at this particular part here, you'd have called 0.3, maybe something like 0.5 perhaps, you could have done that. I wouldn't say that would be a brilliant idea. The reason is because this 0.3 was pretty specific in terms of the multiple, okay? So I would be less inclined to round that. And it's just a hunch that I have, because this is really important, crucial information. It's saying that it's 0.3 times bigger. But then on the other hand, I don't see anything against saying 0.5 if that helps you. And if you had have said 0.5, then that also would have been an overestimate. So if you're using a number which is higher than what you were given, you're going over what is needed. And if you're rounding down to something, say here, you could have quite easily have chosen that to be 1.5 or 1.8, then that would be an underestimate because you were going underneath what was given in the question. It's really as simple as that. So let's move on to another question. Now, this is the last, one of the last questions I would have tried on this paper, that's for sure. I would have probably dreaded this kind of question. Why? Because it has all the ingredients of something where you can make mistakes. You've got to interpret the words. That's not necessarily a strength for me. The more words there are, the more confused I can get, to be honest with you, and some of you may feel the same. Some of you may love these type of questions where you have to just pick through them and pick out the parts. For me, they're my least favourite. But let's try and make good of the question. It says, at the end of 11 games, the mean score. So the way I imagine it is that I'll have the games here from game 1 to game 11, and I'll divide by 11 and I'll get somehow 33, because that's how you get the mean. And so I can work out that the games added together would be 11 times 33. And how did I get that? Well, I just multiplied both sides by 11. So I know that. And then at the end of 10 games, so if I had just 10 games here, divide that by 10 to find the mean, it says the mean was 2 points higher. So that would give me a mean on this side of 35. And then likewise, I could times both sides by 10 and have G1 up to G10 is 350. So if I've got G1 up to G10 is 350, but G1 up to G11 is 1133s. And what's 1133s? Well, it's 10 of them and 1 of them, which is 363. Then you can see the difference between these is indeed 13, and Walked and Reds must have scored 13 points in their 11th game. Jordan is correct, and you just write your explanation below. Okay, but there would be the reasonably good level of workings, and like I said, these are not my favourite type of questions at all, so that's as best as I can do from seeing the question for the first time anyway. Question 10. It says there are some red counters and some yellow counters in a bag. There are 30 yellow counters. The ratio of the number of red, so let's write that down, the ratio of the number of red to yellow is 1 to 6. It tells you there are 30 yellow counters in the bag. And we've got to work out the number of red counters. Well, if the ratio is 1 to 6, then we can treat the ratio similar to a fraction, because if we were to times this number by 5 and be in proportion to this number here by timesing that by 5, then 6 multiplied by 5 would give 30, and 1 multiplied by 5 would give 5. So if you wrote down the ratio 5 to 30, that's really in essence the same as the ratio 1 to 6. Likewise, you could times both sides by 2 and have 2 to 12, for example. One way of helping you remember this is if you took the fraction 1/6, you could make equivalent fractions in exactly the same way. For example, and that's one way of helping you remember how to work with ratio. So it seems the answer here is 5 red counters. Now some more counters, and it says more red counters are put into the bag, and the ratio now between red and yellow counters is 1 to 2. So if you think about it, that means for every 1 red counter there's twice as many yellow. Well, it never said anything about putting more yellow ones in, did it? So if there were 30 yellow ones in, and there was twice as many yellow than there were red, then there'd have to have been 10 more put in, because if you took this 5 and added 10 to it, you'd have 15, and you've still got your 30 here. So can you see that 5 and 10 here make the 15? You've still got the 30 here, and the ratio 15 to 30, that's red counters to yellow, would be the same as the ratio 1 to 2, because you could divide both of these by 15 to get there. So that's how I would do that particular question. Question 11. Write down the value of 125 to the power 2/3. Well, I would think of this like so. Now, you'd have to know the rules of indices, which I'm not going to teach the whole essence behind that right now, but if I give you an idea that if you had a to the b to the power c, that's the same as writing a to the b times by itself, times by itself, times by itself, and so on. Well, how many times do you think? Well, yeah, it would be c times. So you would do that, multiply by itself, c times. So what would the answer be? Well, if you had a to the b times by itself, c times, then you'd have to add b up how many times? Well, once, twice, 3 times, and so on. Well, c times. So if you wanted to add the powers, you'd have to do b, add b, add b again, c times, so there would be bc would be the power. And if you think about this with numbers, if you had a to the power 3 to the power 3, for example, then that's the same as writing a to the 3 times itself, and then times itself again. And by the rules of indices, the addition rule, you get 3 and 3 and 3, which is 9. And so the rule is you just multiply these indices together. Now in this case, you do the same, and 1/3 times 2 is 2/3, which you've got here. So back to the question. I would do it this way, because that's exactly the same as what the question has asked. I wouldn't write this. Which again is exactly the same. Why? Because 1/3 times 2 is the same as 2 times 1/3. So they'd be both the same. But in your head, you should be able to work out the cube root of 125, because all that means is something times itself is 125. And that is 5. Because 5 times 5 times 5 is 125. So that's the part inside the bracket done, and all you've got left is the power 2 here, the index of 2, and 5 squared is just 25. So that would be the answer. However, if you did it this way, you'd have to know what 125 times 125 is. Well, I think that would be 15,625, and that would be hard to do in your head, but you'd have to then do the cube root of that, and you just have to hope that you'd have a calculator on you, but this is not a calculator paper, so I don't think many people would know that the answer there would be 25. The only way you could work out is 25 in your head is to say, well, it has to end in a 5, so it would be something ending in a 5 times by itself 3 times. So I'd have the number here, and a number here ending in 5. I could say 20 times 20 times 20, that is 8,000. Well, that's not enough. I could say 30 times 30 times 30, well that's 3 times 3 is 9, times 3 is 27,000, and 27,000 is too much. So I would be able to work it out in my head and say, well, 20 is not enough, 30 is too much, the number ends in a 5, so it'd have to be 25 times 25 times 25. But I don't recommend doing that in the exam. So use your powers wisely and you'll be able to do the question in your head. Question 12. I think these are quite difficult, these types of question. Sean says that the average speed from Manchester to Gretna Green was 40 miles an hour, and you've got some information, and you've got to work out whether Sean was right. He drives at an average speed of 50 miles an hour for the first 3 hours of the journey. So if you're going to look at speed equals distance over time, because miles per hour just means miles over hours, and that's your speed. So you've got a speed equals a distance over a time. So we know that we're going here at 50 miles an hour for the first 3 hours. So we can work out the distance because we know the time taken was 3 hours, and we can multiply both sides of this equation by 3, and we'd have 150 is the distance travelled. So that's going to get you a mark. It says he then has 150 miles to drive to get to Gretna Green, and Sean drives these 150 miles at an average speed of 30 miles an hour. So again, speed equals distance over time. What do we have? We have 150 miles now as the distance. The time we don't know, but we know that it's at 30 miles an hour. So what we can do is one of two things. We can either invert both sides here, i.e. do it to the power -1, and we can say now times both sides by 150, do some cancelling, so t is 5. So what we actually have now is, this is quite important, we have 5 hours for that last part and 3 hours for the first part. So we know we've got 8 hours of total time. So we can work out the average speed because that speed is the distance, the total distance over the total time. Okay, so the distance that we've got is 150 miles, and then it said there's another 150 miles here. So that's 300 miles in 8 hours. So what's 300 miles in 8 hours? Well, that's the same as 150 miles in 4 hours, which is the same as 75 miles in 2 hours, which is 37.5 miles per hour. Okay, per hour. So I'm afraid Sean is not correct. And incidentally, you could have just done this by just halving and so on. A quicker way is you could have just said, I want to get this per 1 hour, i.e. miles per 1 hour, miles per hour, and you could have divided both sides by 8, and 300 divided by 8 would have given you 37.5 straight away. Question 13. It says make k the subject of the formula. Well, that just means you have to have k equals, and then whatever you've got here would be the answer. Another way of looking at it is to isolate the k part here and get that on its own. So write the question out to take ownership of the question, and then we can start from there. First thing to think about is that we have a square root sign here, and we want to unlock this value of k from the square root sign, so we're going to square both sides first. Don't forget, keep our eyes on the target here. So we're going to multiply both sides by 4 now. And that will give us 4m squared equals k cubed plus 1. Again, let's keep our eyes on that. I think I'll get some more space by doing it this way. I'm going to take away 1 from both sides. So I now have 4m squared minus 1 equals k cubed. Now, if we want k, we've got to do the inverse operation of cubing, which is cube rooting. So really, in essence, what you're doing is you're saying to yourself, do this to the power of a third, and then do this to the power of a third. And I think from the previous question, actually, I think that was question 11, if you have 3 lots of a third, well, you know 3 lots of a third is a whole one, and you'd end up with k to the power 1 here, which is just the k that you wanted. And then so your answer would be 4m squared minus 1 to the power a third, which some people would have been taught to write like this, with a little 3 here. That's slightly more old-fashioned nowadays. Okay, so both of those would be exactly fine. Some of you may have spotted that 4m squared minus 1 is a difference of 2 squares, so another answer could be 2m plus 1 times 2m minus 1 here, and alternatively you could have written 2m plus 1 in a curly bracket and then put a square bracket around all of it. That's when you can use square and curly brackets in conjunction with each other, and then just put a third here. So there's plenty of ways of doing it, but any of those ways would be absolutely fine. For this question 14, we've got to solve an equation with 2 fractions given algebraically. We've got to add those 2 fractions, and we know that the sum of those 2 fractions is 3. So somehow we have to find the value of x. So what I'd normally do in this situation is just write out the question again to get a feel for the question. And then we can start having a look at what we've got here. Well, you may notice here that we've got a denominator which has x in both. So there's a common denominator of x. And what I think we can do here is, if we times this one top and bottom by 2, and we times this top and bottom here by 3, then what we've managed to do is get this denominator as 6x and this one as 6x, which means the denominators will be the same, and then we can add those fractions together. So what we'd be left with in this situation is a common denominator of 6x, and then we just have 2 lots of x plus 2 plus 3 lots of x minus 2, and that's equal to 3. And then from here we'd have 2x plus 4 plus 3x minus 6 equals 18x. And the reason for that is because I times both sides by 6x. Then we can do some simplifying, and we'd have 5x, 4 minus 6 is minus 2, and then we get 18x on the right hand side. And then I think what I'd do here is, I'd probably, as I've got more x's on this side, I think I'll take 5x from both sides, like so, and then I'd end up with negative 2 equals 13x, and then I would divide both sides by 13, and then I'd finally have the answer of minus 2/13 equals x. Okay, so the idea behind this type of question is to try and get the denominators the same, get them to match, and then you're well to go, because then you can add the fractions and you can just use your algebra to try and find the value of x. Okay, so that's question 14. Question 15. We've got an algebraic expression here with a numerator which is a quadratic and a denominator which is also a quadratic, and we somehow have to cancel this down into something which has a linear numerator and a linear denominator. So let's have a look at what we have. So I'm guessing here, with the experience that I have, that we just want to factorise the denominator first and see what we get from there. So we'll leave the numerator the same for now. And let's have a look at factorising the denominator. Well, it's definitely going to have two brackets, an x in each, because that would give us the x squared, and then 5 is a nice prime number, so 5 and 1, and they're both positive here, so you don't need a grid or any fancy way of doing this. You can probably do that in your head. So you've got x plus 1 times x plus 5. Now, to cancel this down, one would be expecting the numerator to have one of these brackets in common. Okay, then it would cancel down. So what I suggest you would have to look at is try a grid, put in, say, x plus 1, if you've got a hunch that that could be one of them, and then think, what could you have on this side of the grid that will give this when you multiply it out? Well, let's try an x here, sorry, a 2x here, because we'd have an x times a 2x would give 2x squared. So we can multiply those out, and we'd have 2x squared here and 2x here. Now, because we have a positive one here, we definitely need to have a negative 5 here. And that would give us our negative 5, which is what we have here. And then if we multiplied this x by the negative 5, we would have minus 5x. Now let's see if that's going to work. So we've got the 2x squared, yes. We've got the negative 5, we know that already. Now we're lucky now because we've got 2x and minus 5x, which will give the minus 3x that we wanted. So we can write the numerator as x plus 1 times 2x minus 5 over x plus 1 times x plus 5. And then x plus 1 divided by x plus 1 is just 1, and so our final answer would be 2x minus 5 over x plus 5. So we can see our value of a here was 2, our value of b, negative 5, c, 1 in this case, and d, positive 5. Okay, so that's how we could look at that kind of question. You just have to go with your hunch and then try some working like this to see whether it works out, and if it doesn't, try something different. Try x plus 5 along here instead, and that wouldn't have worked because it wouldn't have cancelled. Okay? Question 16. These graphs show 4 different proportionality relationships between y and x. Well, let's have a look at this one first. This seems to be the easiest one, and it seems to say here that as x increases, so does y. And there seems to be a direct relationship between x and y. So let's have a look for that. Here we go. Y is directly proportional to x. So we can definitely say that that is D. Let's have a look at something we have seen many times, and that is y equals x squared. So it may not be y equals x squared exactly. It may be of the family y equals k x squared. Now that's the whole idea behind proportionality. You try and find this value of k if you remember rightly. Now what this does show is that there's a direct relationship between y and the square of x, or x squared. So we want to look for that here. So here we go. Y is proportional to the square of x. Okay, so let's have a look at that one, and that would be graph B. Now notice I'm trying to do these in the order of I think is easiest. Now, that's a good way of doing it because then that will leave one and then that will be the last one that's not been filled in. So for this one, you can see here when x is positive, as that increases, y decreases. And here also, as x increases from a largely negative number, like negative 100 for example, as that's getting bigger, negative 80, 70, 60 and so on, then y is decreasing. Okay, so for example, you can say that x was say negative 100 here, and as you move to this side here, to the right, you're getting more and more and more, x is increasing and y is decreasing again, just as it was doing here. X was increasing, y was decreasing. So there's an inverse relationship here, and you may have seen this one as well, y equals 1 over x. This may or may not be 1 over x, but it's of the family k over x, where k is some value. Now, what I would say here is this is not a direct relationship here, because as one gets bigger, the other gets smaller. So it's an inverse relationship, and I would say it's as y is inversely proportional to x. And we've got that here. Y is inversely proportional to x. So that will be graph A. And that just leaves C for this one. But let me try and justify that, because you may have chosen to look at that one first. Well, let's just say we had a value here of, say, negative 2, and here, symmetric to that, 2. And let's say here we had a value, say, negative 4, and here 4. Well, it seems as though when x gets larger, y gets smaller. And here, it seems to be that when x gets larger, y gets larger. So that seems to be a bit of a contradiction. But let's have a look at the language used here. Y is inversely proportional to the square of x. So we're allowed to do this in the exam. We're allowed to say, okay, there's an inverse relationship between y and x, and it's the square of x here. So really, as x gets large, y gets small, and that seems to be the case here. However, with this one it seemed to be the opposite, didn't it? But don't forget, if x is a negative number, if you square it, it becomes a positive number. So if you took x is negative 4 and you put it into here, you'd get negative 4 all squared, which is 16. So a 16th, for example. And that value there would be 1/16. But if you took 4 and did the same, you'd get 16th also. So the complicated thing to take on is, although x is increasing in its size, you have to square a negative number, and if that number increases in size, say for example here where it's negative 1, if you square that, you're going to get a positive number, but you're only going to get 1. Whereas if you started with a smaller number, i.e. x is negative 4, if you squared it, its sign would change to positive and you'd end up with a bigger number. So that's kind of like the contradiction here, and that's quite difficult to explain, but really one way of looking at it is to just put numbers into what the language actually says, and then if it matches the graph, which in this case it does, because you've got this symmetry here, then you can see that this must be the one. But I'd have definitely left that one till last, because these ones are much easier to work out. Question 17. you have to try and prove that triangle Q to T to R, this triangle here, is congruent, i.e. exactly the same as triangle RSQ. So R to S to Q. Now what I always do is I try and always draw the shapes separate from the diagram. So let's have RSQ here. Try and make that a bit neater. Right, there we go. And let's draw QTR as well. Now, let's have a look what we've got. We've got PQ is PR. Now to me, for a moment that seems a little strange, but then I thought to myself, well hold on, that just means that this triangle PQR, the large triangle, is isosceles. It's saying that these are the same. So we know that the base angles, i.e. this angle here, is the same as this angle here. So we can say that angle S to Q to R, this one here, is exactly the same size as T to R to Q, this one here. So I'm going to put a little green dot in there. So they're the same. It says that also S is the midpoint of PQ, so that's halfway here, and T is the midpoint of PR, so that's halfway also. Now this seems rather easy because that means that P to T is the same as T to R. That's important. And don't forget, this whole length here, P to R, is the same as P to Q. So that should mean that this is split in half as well. So S to Q must be the same as T to R. Now, can we have enough information here to prove that triangle QTR is congruent to triangle RSQ? Well, I would say yes, we have enough information, because the nice thing is that Q to R is common to both the triangles that I've drawn here. So we can also say they are the same. And then if you know your proofs here of congruence, one of them is side, angle, side, i.e. side, angle, side, and then side, angle, side, and they correspond. This one to this one, this angle to this one, and this side to this one. But diagrammatically, I just want to explain it in a slightly different way, and that is, if you have a common base here, and you raised this arm here, R to T, for example, up by this angle, then if you think about it, you had the same base here, and you raised QS, which is the same length as RT, up by the same angle. So this final length here would have to be the same, wouldn't it? So therefore, all the lengths would correspond to each other, and therefore the triangle could not be an enlargement because the lengths rather of the sides were fixed. They did not change. So when you were coming to do this in the exam, I would say that you would definitely mention the words isosceles, and then use, for example, base angles of isosceles triangle are equal, and then go on the points here about S and T being the midpoints, and then having that link between TR and SQ being the same length, okay, because of the isosceles nature of the triangle. And then you can go on to say about the base as well. And I'm not going to write all of that out on one screen because it can be quite muddled. What I want you to understand is, the thing I'm trying to help you with the most is to understand that when you do these questions, try and draw out the triangles or the parts of the proof separately from the big, rather complicated initial diagram. That's the thing I'm trying to help you with. The rest, you're going to have to just look at each part and just read the question because it's giving you all the clues that you need. Okay, so you've got to come up with your own ways of really proving things, and I'm just going to outline in this question how I would have done it in the exam. I would have put a few more keywords in, and I'd have written in probably full sentences. Okay, so have a go at that one yourself in a few days' time and see if you can actually do it from scratch. Question 18. It shows a solid hemisphere, i.e. half of a sphere, and it says the volume of the hemisphere is 250 pi over 3. Okay, and that'll be in units cubed. It gives us that the volume of a sphere is 4/3 pi r cubed. So the volume of the hemisphere in this case would be a half of 4/3, which is 2/3 pi r cubed. Now from this we could just cancel through by pi both sides, that's dividing both sides by pi, times both sides by 3, and we would end up with 250 equals 2r cubed. Divide both sides by 2, and we'd be left with r cubed is 125, which means that r would be 5, because 5 times 5 times 5, i.e. the cube root of 125, is 5. So that's quite important. It then wants you to work out the exact total surface area. Well, you've definitely got here a circle of radius r, so the area of that part is pi r squared. So you've definitely got the surface area has that part to it, so it's going to be pi r squared plus, we've now got the curved surface area of the sphere, the hemisphere. So we've done the flat part, we're now doing the curved part, and it says the surface area of a sphere is 4 pi r squared. So of the curved part here, we're just going to have 2 pi r squared. So we're going to add that to it, and that gives us 3 pi r squared altogether. But we already know what r is. R is 5. So we can say the surface area is 3 pi times 5 squared, which is 3 pi times 25, which is simply 75 pi, and we can just say units squared here. Question 19. We've got to simplify a fraction, and there are surds in the numerator and there are surds in the denominator. The first thing to see here is that we have a minus b times a plus b. So we really should be looking for a difference of two squares, a squared minus b squared. So that can be of use to start with. So if we write out the question like this, and we can then directly go to this a squared minus b squared. So we'd have a, which is 6, so we'd have 36 minus root 5 all squared, which is just 5, over root 31, which we've not done anything to. So 36 minus 5 on the numerator becomes 31. And then you may have heard of a topic called rationalizing the denominator, and so we'd just times the denominator by root 31, which means we'd have to times the numerator by exactly the same, And for those that worry about that, you're just timesing by 1 because root 31 over root 31 is the same as timesing by 1, which means that this quantity does not change its value. But what you do end up having here is 31 lots of root 31 over root 31 times root 31, which is 31. And then look what happens here. 31 divided by 31 is just 1, and we're left with the answer of root 31, which is a nice and compact answer, and it looks much better than this, doesn't it? Question 20. Prove algebraically that the difference between the squares of any two consecutive integers is equal to the sum of these two integers. So let's look at consecutive integers. So let's say n is a nice integer. The next one you could write as n plus 1. The next one n plus 2, and so on. You could also go backwards here and have n minus 1, n minus 2, and so on this way. So they're the integers. Now, and they're consecutive, but it said it wanted something about the difference between the squares of any two consecutive. So let's choose two consecutive ones. Let's choose this one and this one. We could have chosen any two as long as they were next to each other, and we're going to square them. So we'll take this one and square it, and we'll take this one and square it, and then it wants the difference between them. So we can do that also. Now, if we had this number here, it would be greater than this number here, wouldn't it? Because it's one more. So if we want to find the difference between them, say if you wanted to have the difference between, say, 8 and 7, you'd say the difference was 1. So you do 8 take away 7. So we're going to do n plus 1 all squared take away n squared. Now don't forget, when you're doing n plus 1 all squared, you can do a little grid. A common mistake is to think n plus 1 all squared is just n squared plus 1. Well, it isn't, because you've got n squared, the 1, but you've got an n here and an n here. So you actually end up with n squared plus 2n plus 1 minus n squared. Well, the nice thing about this is that this cancels with this, and you're just left with 2n plus 1. Now you've got to see whether that is equal to the sum of these two integers that you started with. Well, you started with n, and you had the next consecutive one, which was n plus 1, and if you add those together, you get 2n plus 1, which is exactly the same. Now, I've written this out in a way which I may have not done in an exam, because I wanted to try and explain it to you, but if you just set your workings out just a tiny little bit differently to how I've done, you'd get all the marks. But as long as you show exactly each part, so what you could do for your exam is definitely show this part here, and then get to this answer, and then separate this part off as being the second part, and just maybe write a little bit of an explanation by each part and how you chose it. And then you'd get all the marks. So it's not too bad, and I think you should try and practice some of these, and hopefully more of these will come up at a later stage, and I'll be glad to cover them. Question 21. There are 10 pens in a box, and it says there are X red pens in the box. All the other pens are blue. It says Jack takes at random 2 pens from the box, and find an expression in terms of X for the probability that Jack takes 1 pen of each colour. Give your answer in its simplest form. Well, if you want to take a pen of each colour, then let's just get these colours ready here. So you could either take a blue for your first choice and then a blue for your second choice. Or you could take a red for your first choice and a red for your second choice. Okay? So let's have a look at taking blue first. Well, if there are X red pens in the box, then as there are 10 pens in the box, how many of them do you think are blue? Well, it'll be the 10 with the X taken off, wouldn't it? So we'd know that to take a blue would be 10 minus X, that's how many blue there'd be, over 10 pens altogether. Okay, so I'll go through that again. 10 pens in the box. If you take the red ones away, then that would give you the blue. And as you're picking your first blue pen, that's how many you've got to choose from. So you've got 10 minus X of those blue ones to pick out of 10 pens altogether. When you come to do your second choice, however, there's not going to be 10 pens to choose from. There's only going to be 9. And as you've already chosen a blue, then think how many blue pens are there going to be? If there were 10 minus X of them to start with, there's going to be one less than that, which is 10 minus X minus one more. And yes, we know we can write that probably as 9 minus X over 9, and we'll come to that a bit later. So that's one potential outcome, blue, then blue. If we do red, slightly more easy, we can have 10 to choose from in the box. And how many are red? Well, just X of them. And then for your second choice, you have 9 pens to choose from because you've already chosen one. And this time, how many red? There'll be X minus 1. So when we come to look at the outcomes here, and I'll just change the colour here, we could have done this on a tree diagram, but I've just done the individual branches separately. For this outcome, we would have 10 minus X over 10 multiplied by 9 minus X over 9, and I'll put brackets around here because I don't want to get any confusion, and we'll look at that later. And then for this particular part of the branch where they were both red, we would have had X over 10 multiplied by X minus 1 over 9. And to get both the same colour, we would have to pick this and add it to this. Okay? The ones we won't be looking at is blue, then red, and then red, then blue. Okay? We didn't pick those, but if we added all those outcomes together, blue, 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 red, 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 blue, and we added them all up, it would sum to 1, because it would have to be certain that we'd pick 2 of some kind. So in this case, if I want to add these together, well, I want this one and this one, so I can look at the numerators here, and I can say I've got 10 minus X times by 9 minus X over 90, plus, and then we've got this one now, X minus 1 over 90. Notice that I have a common denominator of 90, which is useful. And then it does say put it in its simplest form here. So let's just see what happens. I'm not one for usually multiplying things out without thinking in advance, but we'll give it a go and see if anything cancels and see where we end up. So let's have a look what we have on the numerator. So I'm going to multiply this all out. So I'm going to assume that at this level you can do this. So we're going to have 90 minus 19x plus x squared minus x. And then we're going to have 2x squared minus 20x plus 90. In this question, we have CAYB is a quadrilateral, and that's from here to here and so on. That's a quadrilateral, and it tells us what CA is as a vector, CB and BY. It says X is the point on AB such that AX to XB is in the ratio of 1 to 2. So if we put X, say, here, then what it's saying is that A to X is 1 part, as X to B is worth twice as much, i.e. 2 parts. So what I'll do is I'll just put the X here, and I'll mark a spot, a point here, and then we'll have AX and then XB shown. And what I'll do is I'll put in a different colour here a 1 part to 2 parts. So if you think about it, A to B is now split into 3 parts. So keep that in mind also, that's really important. We've got to prove that C to X is 2/5 of C to Y. Well, let's start having a look at what we've got. We can firstly have a think about finding C to X. Now if we want to do a journey of C to X, like so, not a brilliant dotted line there, but it will do, then we can say that the journey is C to A plus A to X, and that's the same as C to X. So let's write that down. C to X is the same as C to A plus A to X. Now let's have a look at C to Y here, and I'll do this in red. So if we have C to Y, like so, then we can say that that journey from C to Y is the same as C to A plus A to Y. So we can write that down also. Like so. Now one thing I can see is that A to Y can be found. Now A to Y would be the same as A to C plus C to B plus B to Y, and we can write that out, and we can have minus 3A because it's going in the opposite direction, and we'll underline that. We can't write it in bold, plus 6B plus 5A minus B. Okay, so I've really just done that journey from there to there to there. It's the same as from going from there to there. I can now simplify this, and I'll have minus 3A plus 5A is 2A, 6B minus B is 5B. So that's one element here, so I'm on my way to finding CY. Another important element is to find A to B. Now A to B is the same as A to C plus C to B. It's the same journey. So we can have a look at AC plus CB, and that's just minus 3A plus 6B. So now we have all the ingredients we need to go for it now and prove once and for all what is needed, because we now from here have C to X is C to A, which is 3A, plus AX. Now this is the important part about the ratio to start with, from a to x is one part out of three parts of what a to b would have been. So think back to when I started the question. We looked at the ratio and we wrote the 1 here and the 2 here, which splitted it into three parts because we followed that ratio. And this is the bit which makes this the A star for me, is to recognise that from a to x is literally 1 out of 3 parts of AB, i.e. a third of AB. So a to x is 1/3 of a to b, and we know what that is, it's just there. So we've got minus 3a plus 6b. Now we can neaten that up a little bit. So we'll get minus a here plus 2b, which is 2a plus 2b, and always take out the scalar part here, i.e. the part that has no direction, and we're left with a plus b, which is the vector part which has the direction. So we have what c to x is, which is really good. Now all we have to look at is c to y, and we've got ca again, which is 3a plus ay, which we had here. And neaten that up, and we have 5 lots of a plus 5 lots of b. Take out the scalar part and leave the vector part intact, and so we have cy. Here we had cx, and now we can make our final conclusion here, and we can say here that from here we had cx equals 2 lots of a plus b, which would mean that cx over 2 equals a plus b. From here we can have cy over 5 is a plus b also. And if you think about it, that's worth a plus b, this is worth a plus b, so that would mean that this is equal to this. And if we write that, then we can have multiplied both sides by 2, and we end up with cx equals 2/5 of c to y, which is what we needed to prove. Now, that's a reasonably long way around it. However, that's me seeing the question for the first time and trying to explain it as well. I think if I was doing that in the exam, I'd probably go a little faster, maybe do a few shortcuts, and if you can see those shortcuts, this is part of your revision. You don't have to copy or emulate exactly what I am doing. You can look at what I'm doing and then maybe try and see another way to the same answer. And that's really what maths is all about. It really isn't just trying to repeat something. You've really got to take it on yourself and take ownership of the question. And then you'll definitely have success. That I can definitely tell you. Okay, so that's question 22. Question 23. Find an equation of the line that passes through C and is perpendicular to AB. Well, this is quite tricky, and with my experience of 20 years in the classroom, I can tell you now that students find straight line questions by far the most difficult. That and percentages usually. So if we look at coordinate A, just write that down, we know it's -2, 0, and B is 0, 4. So we can find the gradient of this line by comparing the y's and the x's. And the gradient in A level is usually looked at as dy dx, so we want to look at the rate of change of y over the rate of change of x. Now, that's a little bit complicated for GCSE, but if you try and look at it as the steepness, so if you have a straight line with a certain steepness or gradient, then if you journey along it 1 unit, however much you go up is basically your gradient or your steepness factor. Okay, so always think about going along 1 unit and see how far you go up. So one way around that is to try and think of this is the change in the y and this is the change in the x. Okay, and it doesn't have to be 1 unit on the x, but you can always scale it down to 1 unit, and I'll show you how this works with these two coordinates. First thing you have to ask yourself is, how do I compare 0 and 4? Am I going to do 0 take away 4, or am I going to do 4 take away 0? Well, once you've decided how you're going to compare the y values, you must do exactly the same way for the x values. That's all you have to remember. So we're going to write m, ab, which stands for the gradient of ab, and we're going to do 4 take away 0, that's the change in the y, and then we're going to do 0 take away negative 2. Okay? And what do we end up with? 4 divided by, well, 0 minus minus 2 is 2, and 4 divided by 2 is 2. Then we do a quick check with the diagram. Is this line going uphill? Yes, it is, so 2 makes absolute sense. Now, you might argue, well, what's this got to do with what I said here about going along 1? Well, if you divided this denominator by 2, you'd make that 1. And as long as you did the same to the top, you'd end up with here 4 divided by 2 on top, which is 2, and you'd have your 2 divided by 2, which is your 1. So what you're really saying is, for every 1 I go along, I'm going up 2. And that's really, in essence, what a gradient is. So we know the gradient of AB, and it says that the line passes through C and is perpendicular to AB. Now, hopefully, you've been taught this, and I won't have time to teach you all of these skills throughout this paper, but I have done some videos on these particular topics, and I'll try and put links on as many questions as I can if I have the time. So basically, if the gradient of this line segment is 2, then to be perpendicular, it's going to be going downhill, so we know it's going to have a negative gradient, okay? And the way of doing it is, if you have two lines that are perpendicular to each other, if you take the gradient of one of them, say m1 for this one, and then you take the gradient of the one perpendicular to it, what you can do is, and there's a nice thing that always works every time you have two things that are perpendicular to each other, if you multiply the gradients together, they'll always equal a certain number, and that number is always negative 1. So, in this case, if we had the gradient of the line segment AB, and that was 2, we'd have to times that by something that gave us negative 1. Well, the only thing I could times 2 by to give negative 1, well, think about timesing something by 2 to give 1. That something would be a half, or the reciprocal of 2. So that would be 2 times a half, which would be 1. So we know the gradient's got to be going downhill because this one went uphill. So the gradient of the line perpendicular to the line segment AB must have a gradient of minus a half. So we know that this line has a gradient here, and we can say gradient of C, and we can say that is definitely minus a half. So what else do we know? We know that the line passes through this point here as well. Well, that's a nice thing, because you've either been taught by your teacher that you can have the equation of a line which is y equals mx plus c, or the way I teach my year 11s is I have y minus y1 equals m x minus x1, and I definitely have a video on that. If you look in one of the playlists under straight lines, I think you'll find a video explaining where that comes from. It's quite straightforward. And all you have to do is, and I'm going to use this method, is you put in the things you know, and then what comes out is the equation of the straight line. So the first thing we know is this. We know the gradient of it is minus a half. We also know a y value. We're given it, minus 1. And we're also given an x value as well, 5. So really what we have is y plus 1 equals minus a half lots of x minus 5. Now we usually write in GCSE y equals mx plus c the form, so I'm going to take one from both sides. So I'm going to have y equals minus a half x minus 5 minus 1, and I'm just going to multiply out this bracket. So I'll have minus x over 2 plus 5 over 2, because a minus times a minus is a plus, minus 1, and I'm calling that 2 over 2 to get the denominators to match. So I'm just left with minus x over 2 plus 3 over 2, and that's y. So my equation of my line is y equals minus a half x plus 3 over 2. Okay, now at A level, you can write your line in this way. You can say 2y equals minus x plus 3 by timesing everything by 2, and then you could add the x to both sides and have x plus 2y equals 3, and then take the 3 from both sides and end up with x plus 2y minus 3 equals 0, and that would be your form of your straight line. So there's many ways of writing a straight line form, but at GCSE, stick with y equals mx plus c. Incidentally, if you wanted to use this method to do this question, then all you'd have to do is put the value of m in that you have, which is minus a half, put in your value of y, which was negative 1, put in your value of x, which was 5. That would then help you find the value of c, and once you've got the value of c, you just write y equals a half x plus the value of c that you just found. Okay, so give that a try and then see how you get on. If not, ask your teacher to go through it again in class, because straight lines can be quite tricky. But we're bound to come across quite a few more, so we'll see how we get on as we go through these papers.